Today we're going to be reviewing electric force and electric field, chapter 21 in your textbook. Everything that I'm going to be going through today should be a review from last year, so I'm going to go through it rather quickly. The electric interaction, as far as we're concerned, is a field interaction. In other words, it does not require contact. This is what we're going to assume to be true, although once you start studying quantum electrodynamics in college, you're going to find out that it's something different than what we're studying. But for now, it's good enough to say that this is an interaction. The electric interaction is something that does not require contact between charges. It depends on electric charge, which is a physical property determined by the motion of electrons. So if something has more electrons or something has less electrons, then that's going to affect its electrical charge. The other thing you should remember about the electric interaction is it weakens with distance, and we'll see in Coulomb's law how it does so. Some basic knowledge that you should have is that electrons repel electrons, and of course electrons attract protons. There are a couple different kinds of electric interactions. One is a strong interactions where like charges repel and opposite charges attract. The other type of interaction, which is a weaker interaction than that, is that neutral objects polarize and attract charged objects. So last year you may have studied that a balloon sticks to a wall. The balloon is charged and the wall may be neutral, but the wall gets polarized and therefore attracts the balloon. If you don't remember anything about the electroscope, it may be worth reviewing your notes from last year or look through sections 21-1 to 21-4 in your textbook. You do need to have this base knowledge, but I will not be going through this. What we will be studying for a while is Coulomb's law. Coulomb's law defines the electric force that one point-like charged object exerts on another point-like charged object. The vector equation is given in this format. F, the force on Q1 due to Q2, is equal to K Q1 Q2 over R squared. And you'll notice a little addition this time at the end, which is R hat from 2 to 1. This actually gives the direction of the vector. So if we have charge 1 here and charge 2 here, R21 is a vector that goes from 2 to 1. So this is R21. It has magnitude and direction. The magnitude is just that distance, so that's what shows up in the denominator here. And R21 has a direction given by R hat. R hat is a unit vector, so it has magnitude 1, but it has direction. So vector R21 is pointing in the direction of R21 hat. It just so happens that R21 hat has magnitude 1. So what is this R hat doing here? It doesn't actually change the value or the magnitude of the force. What it does is give us a way to express the direction of this force. So let's say that if charge Q1 is positive and charge Q2 is also positive, then this number will be a positive value, and therefore the force on Q1 due to Q2 will be in the same direction as R21. So that would mean that the force would be going this way, if this is positive. However, if Q1 is positive, but Q2 instead is negative, that would make this value, the magnitude K, Q1, Q2 over R squared, that would be negative then. So R21 have to take the opposite direction, and that would give us the force. So if plus minus. So this unit vector is just a way to embed the direction into the vector version of Coulomb's law. We're actually not going to be using this vector version, but I thought I'd throw it out there just so that in the future, when you see it, it's not a surprise. At this point, we should also address the units that are involved in Coulomb's law. So the force, of course, is in newtons. The charges, sometimes they're capital Q, sometimes they're little q. The unit of charge is going to be in coulombs. R is obviously going to be in meters. That makes K in Newton meters squared per Coulomb squared. It's also worth noting that when we use Coulomb's law, we can use this value K. Sometimes they indicate it Ke, the electrical constant, versus a spring constant. But this K, we're going to start writing it a little bit differently. We're going to start writing it 1 over 4 pi epsilon naught. Epsilon is a constant that kind of defines things about free space. It's called the permittivity of free space. And we're going to be seeing it with regards to a couple other equations, so we might as well start using 1 over 4 pi epsilon naught instead of this electrostatic constant K. The value of this permittivity of free space, epsilon naught, is equal to 8.85 times 10 to the negative 12th, and the unit they usually give is farad per meter. So we'll learn about what that means later, but you know that if you put in these numbers for 1 over 4 pi epsilon naught times the quantity Q1, Q2 over R squared times R hat, then you are going to get newtons on the other side. Something that you definitely should remember from last year is the principle of superposition. It says that if there are multiple point charges, the resultant force on one particle is the vector sum of the individual forces on that charge. Let's look at an example. If there are 3 charges in the line and we want to find the force on particle 1, what we could do first is look at the interaction between particle 2 and particle 1 and sort of ignore that particle 3 exists. So if we were to draw a free body diagram of particle 1, then since particle 1 is positive and particle 2 is negative, we're going to see that particle 1 is attracted to particle 2. So this is the force on particle 1 due to particle 2. And we can calculate this force using Coulomb's law. So the magnitude of force 1, 2 is equal to K Q1 Q2 over R 21 squared. And that's just the magnitude of it. We're going to ignore that R hat. Now let's use the principles of superposition and look at the interaction just between particle 1 and particle 3. Here we can actually ignore the interaction between particle 2 and particle 1. The interaction between particle 1 and particle 3, since they're opposite charges, is an attractive force. So particle 1 is actually going to be pulled to the right by particle 3. I can tell right away here that the force F13 is actually going to be bigger in magnitude than F12 because charge 3 is bigger than charge 2, and it's also closer to charge 1 than charge 2 is. So I'm going to draw this vector bigger, and this is going to be F13. Okay, so we can also find the magnitude of this force by using Coulomb's law, K Q1 Q2 over R21 squared. I forgot to mention earlier that our constant K is equal to 9 times 10 to the 9th. And what are the units here? This is Newton meter squared per Coulomb squared. So 9 times 10 to the 9th should be easy to remember. We're going to use that as K. So in order to find the net force on particle 1, I can write that sigma F is equal to F13, the magnitude of it, minus F12. And when I plug in numbers, what I get is 5.7 newtons to the right. Let's take a look at another example. Here we have to find the force on particle 1. So again, what we're going to be doing is drawing a free body diagram of particle 1. I'll draw it here. And using the principle of superposition, we're going to just look at the interaction between 1 and 2. Since that is an attractive interaction, since 1 and 2 have opposite signs, then we know that the force on particle 1 is going to be in a direction towards particle 2. So let me draw that like this. Force on particle 1 due to particle 2. Then, using this principle of superposition again, we're going to look at the interaction between 1 and 3. That, again, is an attractive force. So, the force on particle 1 due to particle 3 is going to be to the right. In order to find the net force, we're going to have to add these two vectors with components. And I can draw the resultant here by using the parallelogram method. This is going to be, let me make it a little bit thicker so that you can see it. This is going to be the direction, roughly, of the force on particle 1 due to both of these charges. So pause this video for a second and, using Coulomb's law, calculate the magnitude of the force on particle 1 due to particle 2, and then the magnitude of the force on particle 1 due to particle 3. Add them vectorially using component vectors and Pythagorean theorem, and also find an angle that this makes to the horizontal. If you did that correctly, you should have gotten the answer 23 newtons at about 24 degrees above the horizontal. As we said, the electric force is a field force, so objects do not have to be touching in order to interact. We're at least going to try to find a mathematical way to explain the mechanism behind this, and by doing that, we're going to try to define the electric field. In math, a field is anything that is defined at every point in space. So, for example, there is a temperature field in the room you're sitting in. Perhaps closer to the windows, the temperature might be lower, or towards the floor, the temperature might be lower than at the ceiling. But regardless, every point in space in this room has a value of temperature. Likewise, near electrically charged objects, we can define a number in every place in space around those charges. Even more than that, an electric field is a vector at every point in space. So not only does every place in space around charges have a magnitude, but it also has a direction of the electric field. For example, if we have a point charge, like a positive point charge here, we can define every place in space by with an electric field. The direction of the electric field is defined as the direction of the force that a positive test charge would feel if it was placed in that location in space. If we put a charge in this place in space, it would feel a force, a positive charge would feel a force away from the charge, a repulsive force. If we put a positive test charge in this location in space, it would also feel a repulsive force away. But notice that the magnitude of these vectors has to do with the relative magnitude of the force that this test charge will feel. Here, closer to the source charge, the test charge will feel a greater force than if the test charge was placed here a little farther away. In order to calculate the magnitude of the electric field around a point charge, we're going to be taking a look at Coulomb's law. So the electric field quantity is actually embedded in Coulomb's law itself. So if we took Q2 to be our positive test charge, we could say that for every unit of charge that you placed at a particular location in space, it would feel a certain number of newtons depending on the electric field. That electric field is embedded here in Coulomb's law. So if we knew the electric field at a particular position, we would know that if we placed a charge, Q2, in that space, we can multiply it by the electric field value and get the actual force. So in a way, the electric field is kind of like a multiplier. In order to get electric field, we multiply the number of coulombs times the electric field value, and we get the force in newtons. The previous equations are true only when we're talking about point charges, but a more general definition is this, that electric field is defined as the force per unit charge. So actually the electric field units are newtons per coulomb. This definition is always true, so we can use it no matter what our electric field looks like. However, this equation here, where we say that the electric field is equal to KQ over R squared times R hat, this actually should be a vector E. This is only true for a single point charge. But we can also use this formula for a single point charge in conjunction with the principle of superposition in order to get some more complex electric fields. Here's an example problem. In part A, find the magnitude and direction of the electric field at corner C of the square. So notice that there doesn't have to be a charge in order to have an electric field at this location. Remember that the electric field is just a property of that place in space, that if we put a charge there, it would feel a certain force that was proportional to the electric field depending on the charge. So what we have to do first is imagine that we put a small positive test charge at point C. What would be the directions of the forces on that positive test charge? Well, due to particle A, since particle A is a negative and we're dealing with a positive test charge, opposites attract, and the test particle at C would be attracted to the particle at A. So the electric field due to A would be down and to the left at an angle of 45 degrees from the horizontal. So this would be 45 degrees from this horizontal. If we look at B, since B is a positive charge and C is a positive charge, this would be a repulsive force. So the electric field due to charge B would point to the right. Likewise, the electric field due to point C would point up. So we can actually use our equation that we just saw, that the electric field is equal to K, or 1 over 4 pi epsilon naught, times Q, that's the source charge, over R squared. We're going to do that. We're going to use this formula for each one of these, taking note that the R value for the electric field due to A has to do with this particular distance, which will be 5 square root of 2 centimeters, using what we know about the 44, 45, 45, 90 triangle. If you plug in all those numbers, you should get an answer of 1.5 times 10 to the 6 newtons per coulomb at 45 degrees. So that means that E and B together sort of dominated EA. So the ultimate direction would be up and to the right. In part B, what charge QC should be placed at corner C so that the net electric field at the center of the square is 0? Now we're looking at a different place in space. So we could draw a little sort of free body diagram-ish thing, although it's not really forces, now it's electric fields. But we're going to pretend that we put a small positive test charge at the center. This positive test charge will be attracted by particle A, repelled, so this is EA, it'll be repelled by particle B, it'll be repelled by particle C, oh, so this is D actually. Notice that the electric field due to D and the electric field due to B are going to completely cancel each other out because they're 180 degrees from each other. Likewise, the electric field due to C is going to have to completely cancel out the electric field due to A. So EC is going to have to equal EA. So just by inspection, we can see that the charge at corner C is going to have to be -2 microcoulombs. The final part of this problem asks, determine the magnitude and the direction of the force exerted by the 3 charges at A, B, and D on the 4th charge C. So we're going to say that this charge here is 2 microcoulombs, and those will be -2 microcoulombs. And we're going to try to find the force on that particle. Now, one way to do it is actually to draw an actual free body diagram of the -2 microcoulomb charge. We know that it's going to be repelled by particle A. It's going to be attracted to particle B. And it's going to also be attracted to particle D. But there's definitely an easier way of going about solving this problem. We already know that the electric field at that location is 1.5 times 10 to the 6th newtons per coulomb at 45 degrees. We found that in part 1. So we can utilize this information to get the magnitude of the force by using the definition of electric field. So we can say that the force is going to be equal to QC times the electric field. So the magnitude is going to be 3 newtons, and the direction is going to be 180 degrees from the 45 degree bearing. because it's a negative charge. So remember, electric fields are defined in the direction of a positive test charge, whereas when we actually put a negative test charge in that location, the force is going to be in a direction opposite the electric field. So ultimately, this particle is going to feel a force of 3 newtons at an angle of 45 degrees below the negative x-axis. So going back to the second problem we had done, in order to find the force on particle 1, we could actually add together the contributions from 2 and 3 like we did in the second problem. But a different approach to that would be to find the electric field at the location where particle 1 is, and then say that particle 1 actually interacts with only one thing, which is the electric field. Instead of saying at this corner that particle 1 interacts with particle 2 and it interacts with particle 3, one way to think about it is that particle 1 actually interacts with the electric field at that location. So a couple notes about electric fields are, first of all, they don't interact with other electric fields. So the electric field is only one value for any one location in space. So we don't say that for one location in space that there's an electric field going up and an electric field going right. We have to add those two together to get the electric field at that point. Electric fields only interact with other charges, so they don't interact with something like mass unless that mass is associated with a charge. Electric fields are invisible, they're massless, they're chargeless, so electric fields aren't charged particles in any way. And are they imaginary? Well, we sort of made up this concept of an electric field because it works in helping us to solve problems. But scientists wondered what an electric field actually was. And in the 1960s, they came up with an answer. But I'll leave that as an exercise for you to find out on your own. If you have any questions about this presentation, please write them down and bring them to class tomorrow. See you there.